This is the first video in a series of videos that are a deep rabbit hole down the idea of solutions, so that is where we are starting off right now. A solution, as you may recall, is just a mixture that's homogeneous at the molecular level. Alright, and what do we mean by homogeneous? That's another vocabulary term from earlier in the semester. In fact, orange would be a bad color there. What do we mean by homogeneous? We mean uniformly mixed. There's a uniform distribution of particles. I guess it's worth mentioning in passing that a mixture is something that can be separated by physical properties. So for instance, you could have salt water and evaporate the water off using its boiling point, collect the solid salt. You could use solubility if you wanted to separate sand and water. You could let the water evaporate, or you could use filtration or whatever. So when you're talking about mixtures, you're talking about things that can be separated based on physical properties. And a solution is a homogeneous mixture that is homogeneous right down to the molecular level. The other vocabulary term right here of interest to us, and we've seen it before, aqueous, and aqueous just means literally in water. And we'll add a little more to that for our purposes. We're going to say it is dissolved in water. I want to throw in a couple of our abbreviations. We're going to get some mileage out of them. Aqueous, AQ, you've seen that before for our chemical reaction types and everything like that. Solution, SOLN. That's one that saves me quite a bit of writing as well. Let's deal then with this idea of what it means to be dissolved. And you've heard of dissolving before, and you've seen this idea of dissolving. If you want to make Kool-Aid, you take a cup of sugar and you dump it in some water and stir, and it dissolves, right? If you're going to make pasta, you take a pot of water and you dump a bunch of salt in, and it dissolves when you stir it, right? Well, both of those things are dissolving. One of them happens to be a special kind of dissolving known as dissociating. And you'll notice here I put 1.5 things that I tell my students all the time. There's no salt in salt water. All right, sodium chloride, table salt, is a strong electrolyte. It dissociates completely. You just get sodium ions and chloride ions, and we're going to see how that works. There is sugar in sugar water, though, because the covalent bonds within the sugar don't break apart. The sugar molecules just get farther apart in the water. So that's what we're going to be looking at as we look more closely at what it means to dissolve. And in simple terms, dissolving is just to separate the particles by overcoming intermolecular forces. And I'm not going to write out intermolecular forces. You've seen it enough. Intermolecular forces. And as a quick refresher, in case you've forgotten, the common types of intermolecular forces we might see: London dispersion forces, dipole, of which you have hydrogen bonding as an option, and then ionic, which is going to be important in its own right in terms of dissolving and dissociating. It's important for us to note, and I said it earlier, when we're talking about dissolving, we are not breaking our covalent bonds. All right, that is not happening. We are overcoming intermolecular ionic forces, though, at times if we need to. Now, if we want to look one step past dissolving, we can look at dissociating. So, a subcategory of dissolving is dissociating. And you can kind of look at the word etymologically and say, oh, I know associate is to make some connection with or to join together, so to dissociate is to separate in some way. In this particular case, we're talking about overcoming ionic attractions to separate ions in solution. All right? So we're overcoming ionic attractions to separate the ions in solution. And there's another name we have for ionic compounds in aqueous solutions, And we should note that we call these things our ionic aqueous, ionic compounds. We might call electrolytes, which is probably a term you've heard from Gatorade or sports marketing beverages, or if you've watched the movie Idiocracy, electrolytes are what plants crave. But we'll go into more detail on that term. The strength of electrolytes determines how good things are at dissociating or dissolving, as the case may be. So we've got this term dissolve, we've got this term dissociate. Now I want to look at these in picture form and wrap this video up as quickly as we can. So the first thing I'm going to look at is sugar. And then the other thing I'm going to look at is going to be table salt. And I don't have a good color coding plan, so we're just going to go with it. Table sugar, sucrose, is C12H22O11. All right? And I'll get tired of writing that, but that is what we have. And I'm going to draw out a crystal. Now, I don't think sucrose is actually a simple cubic structure, but the picture's going to make sense anyway. So if you have solid C12H22O11, solid, it forms some type of cubic structure, and I laugh to call it simple cubic because there are sugar cubes that you can put in tea and things like that. And so what we have in this particular case is some cubic structure, C12H22O11, C12H22O11, and we've got these all the way around. And I don't really want to draw anymore. I guess I'll draw one here, C12H22O11. All right. Now, it's worth noting that there are covalent attractions within this sugar, and then there are intermolecular attractions between the sugars, and those are words that I want very clear on the page here. So there are covalent bonds within that structure, and there are intermolecular force attractions between the molecules. All right, so those are two key ideas that we have there. There's covalent bonds within that structure, and there's intermolecular force attractions between those structures, those molecules. In fact, it would be good perhaps to add molecules. And there's covalent bonds within the molecule. So what happens then when we take our C12H22O11 and put it into water? Well, let's go back to my caveman representation of a beaker here. There you go. And we got water in our beaker. And so what we're going to be looking at now is C12H22O11 aqueous. All right, we had solid there. We're going to have aqueous here. What is the difference? The difference is the distance between the particles. The water molecules get in there. There's some intermolecular attractions. Like dissolves like, and they separate. So I still have C12H22O11. I just don't have it in some specific crystalline arrangement like I did. I've got another one maybe like C12H22O11. Maybe I've got one here, C12H22O11, etc. And they're just in there, floating around. I don't want to draw all five, but that's how it is. So I still have distinct molecules, the C12H22O11s. They're just not locked into place by those intermolecular attractions. Those attractions still exist. They've just been overcome by the attractions to those polar water molecules. So now let's look for comparison, and I guess compare and contrast the sugar with table salt NaCl. And we'll start by looking at NaCl solid. I'm going to draw out our structure, and again, these efforts at color coding aren't super meaningful, but sodium chloride does actually happen to have a simple cubic structure. If you don't know what that means, it affects you 0%. It's just a disclaimer for the people who get obsessed by such details. So there's our crystal lattice, our crystalline structure, and we've got at the vertices of this crystalline structure our sodium ions and our chloride ions. And then there's another one in the back. I guess I forgot to draw my Cl minus right there. And there's another sodium in the back, and I'm not worried about it right now. So what do we have in comparison? Over here we have this ionic attraction pulling the sodium and chlorine together, and right there, that is what we see. So this right here is an ionic attraction. And that's between or among the cations and anions. So when we are overcoming something, we're going to overcome that attraction right there. And if we put this into our beaker full of water, and this time we have NaCl aqueous. Now, we're just going to have our sodium ions and our chloride ions floating around. They're no longer ionically bonded to each other, held in place by those electromagnetic attractions. Na+. The ratio still stays the same, but now you've just got them floating around in whatever arrangement is convenient. As we look at this, you can see that in an aqueous solution of salt, the ions separate into cations and anions floating around the solution. There's no salt left in there, it's just cations and anions. And if we evaporated the water off, the cations and anions would come back together and we'd have solid salt. However, with something like sugar, a covalent compound, we do have those molecules floating around in the water. We've just overcome the attraction between the molecules, not between the ions. So there is actual sugar in sugar water.